Okay, thanks so much. So very quickly, thanks so much for pointing that out. Today we're going to be talking about two experiments, namely Stern-Gerlach and double slit experiment, the point of which is to say that quantum mechanics is inevitable. These are two key experiments that told us about the necessity to abandon the classical point of view and introduce quantum mechanics. So we're starting with the first experiment, this Stern-Gerlach experiment. We're sending some silver atoms or some atoms, as long as they have spin, and through some magnetic field. Because the magnetic field has gradient in the z direction, these atoms will feel a force, which is proportional to the gradient of the magnetic field in the z direction. And if the spin in the z direction is positive, they will bend forward. If there is negative, they will bend downward, upward and downward. So if you have a detector here, you could detect some of them here. You deduce from the experiment that these atoms had positive SZ, and some of them down here, you will deduce that they have negative SZ, Z component of spin. Is that clear? Any questions? So it's a measurement to measure the Z component of spin of an atom. Good. Now, if spin was the same as classical angular momentum, we expect all values of SZ to be realized. So for example, you expect SZ, if S was an angular, like similar to angular momentum, it was a vector in space, some arbitrary vector in space, you project it down to the Z direction, you expect silver atoms, if they are random, this moment is randomly oriented in three-dimensional space, you expect all sorts of various values of the Z component of S the spin are realized. So you expect to see something like this, right? Which is some sort of a continuous spectrum of all sorts of different values of SC. But what we see in experiments is different. We see that either SZ is positive half in units of h bar. H bar is just some number. It has dimensions, or is minus h bar over 2, and nothing in between. So here there's some sort of width associated with these because of the imprecisions of the measurement. This h bar is a constant. It's dimensionful in physics. Do you know what the actual dimensionality of h bar is? Can anyone say what the dimensionality of h bar is in physics?
Joule seconds?
Yeah, it's joule seconds, electron volt second, but the simplest way to think about it is it's the same as angular momentum, right? Spin, angular momentum. So it's like, yeah, it's the same as angular momentum. This is the value of it that I've written in electron volt per second. Electron volt second, sorry, not per second, electron volt second. 6.5822 times 10 to minus 16. It's a very, very small number, but small is relative because it's dimensionful, right? So this is the very first part of this experiment. And the lesson is that spin angular momentum is quantized, right? That's somewhat surprising. If you thought of spin as a vector in three-dimensional space, if you project this vector in the z direction, and this vector is randomly oriented, you expect all values of SC to be realized, whereas we see only the plus half h bar over 2 or minus h bar over 2 in experiments. Is that clear? Any questions? So this is, oh my God. This is the very first surprise. Okay. Now, I think, sorry, I don't know what is going on here. I apologize about that. Sorry, just 1 second. I apologize about that. All right. Any questions about the first part? So we observed that angular momentum is quantized. All right, now let's repeat this experiment. What we're gonna be doing is we're gonna take our silver atoms and we send it through the measure. So this box represents this measurement that I just described, right? So this box is precisely this whole thing. A measurement that measures the positive, measures the SD, and it comes out either as positive or negative. It comes out quantized, right? So I'm just gonna present this. This schematically means the positive values of SC. This is negative value of SC. So in the first step, we measure SZ and discard the cases where the Z component of angular momentum comes out to be negative and only keep the positive one. Okay. Again, we take this positive beam and send it through the same measurement again. It comes out as positive. So that's good, right? So that's good. Now imagine we do this, but in the second step, we rotate our configuration, just the whole thing, we rotate it around the, and instead of measuring the component in the Z direction, we measure the X component of it. So what do we obtain? This, I'm just describing to you the result of the measurement. We first measure SZ, we keep the positive component, the up component of SC, the ones that have positive SC, send it through SX, and we find that, again, both values of up and down for SX are realized. Is that good? Okay. So what would you think at this point we have? We send it through SZ, we keep the positive up component, send it through SX, keep the up component. Classical understanding of physics or reality tells us that what we have, the beam we have here, has the value of +1 for S of Z and value of S +1 for S of X. Does everyone agree with that?
No.
Okay.
I mean, for classical.
Now
yes.
Classic. Now let's test it. We send it through SZ, +1 comes out. We send it through SX, +1 comes out. We're discarding the -1s. Now we send it through SZ again, and we see both +1 and -1 come out. So this is the result of an experiment. There is no way to reconcile this with the classical notion of reality that assumes that this values of SZ and SX take predetermined values. We're forced to conclude that the measurement of SX, quote unquote, destroyed or disturbed the previous information of SX. Okay, so this experiment I'm describing to you guys is an experiment that's done with microscopic atoms. But if you just want to see how crazy this thought experiment is, imagine these measures. We have two different types of apples, green and red. And the green or red apples come either in large or small sizes. Now imagine SZ is the measurement that decides the size of the apple, and SX is a measurement that decides the color of the apple. So you first send your apples through this measurement, you keep the green ones. Then you take the green ones, and out of those green ones, you only keep the small ones. So you would think you would have small green apples. But the problem is that if you test again whether your small apples are green, sometimes they come out red. This is what we're seeing, but in this particular experiment. Is that idea clear?
How do you measure this?
Yes,
What's the detector that actually measures this?
measures what?
The spin?
Sorry, you're asking what is the. So I just described how the detector works, right? So the detector looks for the atom. If the atom hits here, it leaves some sort of a mark, and then we're going to measure that, right? So this experiment measures SZ, whether it's up or down. Was that your question, or?
Well, does it hit the detector? Like, how does it go through kind of a cascade of these?
So this whole measurement, right, is we're just designing a measurement. First, we measure these, right? Like, for example, if it's up here, I don't have to stop the atom. Well, what I can do is that I can put a laser here that measures whether that scatters off light from the atom here and sees whether the atom is up here or down here, right? So you don't have to stop the atom from going. It could be sequential. You send the atom, it bends up. You could scatter a laser light and see whether it goes through here. Then you take these guys and discard the rest and send them through other measurements.
Okay, that makes more sense.
Yeah. Another question? So the second lesson we learned is that not only the values of SC are quantized, but we're seeing that there is a fundamental law of nature that says you cannot simultaneously know the value of SZ and SX. As a matter of fact, we will see later in the course that the system simply does not have predetermined values of S and X, SX and SC. It's not that it's our inability to obtain that information, but there's this beautiful experiment designed by John Bell, the guy I was quoting something by, that makes it crystal clear that in nature, an atom that's propagating here simply, before you measure it, cannot have predetermined values of SX and SC. So that should be shocking. But for now, we're just going to take this experiment as given. We're going to try to come up with a mathematical description, mathematical formalism that describes it. Is that clear? So before we try to come up a mathematical formulation for this, to capture this bizarre behavior of spins, we remember that we've seen something like this before. And this was not in detection of particles, but this was when we were studying waves. So light waves behave the same way in a sense that I'm going to describe now, right? So is it clear what I'm going to describe now? I'm going to describe something similar to this that we've seen and understood in physics before. And then we're going to see that we can borrow the mathematical formulation from there and use it to formulate physics that describes a measurement that I just described. So consider a light beam that you're sending through a polarization filter. So this light beam has an electric field. This is like a photon that's propagating. This polarization is about, so here's propagating the y direction. So the polarization is in the perpendicular direction. It's a two-dimensional vector, right? It's either in x or z or some linear combination of the two. So if E is in the x direction, we say it's polarized in the x direction. If it's in the, oops, sorry, I think this is a typo. If it's in the z direction, this is polarized in the z direction, right? And ky minus omega t here tells you that there's a wave that propagates along the y direction. Is that good? So this is just polarization of light. Now consider three different types of filters. These are Polaroid filters. The X filter that sends through the X polarized light and blocks off the Z polarized light. The Z filter that does the opposite. It sends through the Z polarized light and blocks the X polarized light. And then the 45-degree rotated filter that sends them through with some probability. Is this clear so far? All right. So what's the setup? As I said, if you send your light beam, if you send it through the X filter, what comes out on the other side must be polarized in the X direction, right? It doesn't matter what you send in, what comes out is polarized in the X direction. So if you, I'm sorry, I think these are, I changed my notation, I did not update these. If you send that through a Z filter, no beam comes out, right? That's just sanity check. This was X polarized, so through Z kills it. Now, what we're gonna do is we're gonna first send it through X filter to make sure that it's X polarized, then send it through the 45-degree X prime filter, this one that was this filter, right? And what comes out, we're gonna send through the Z filter. And a B comes out. So just in comparing with what we were saying before, here what happened is that sending the beam through the X prime filter changed the final measurement, right? So we're doing two measurements. All we did was that we did something in the middle. And all of a sudden we got some beam coming out. This is analogous to what we were describing. If we make the following analogy, the SZ being +1 or -1 is whether the light is X polarized or Z polarized. And SX being +1 or -1 is whether it's X prime polarized or X, yeah, they want to, yeah, X prime or Y prime polarized. Y prime is like 45 degrees the opposite, right? Like in this direction, right? So what we are observing is that if you put in the middle some other measurement, all of a sudden the result changes. This is the analogy. Is it clear? Okay. So let's try to make this analogy a little bit more precise. So the way we usually explain this physics of polarization is that we think of them as vectors, right? So the X prime polarized light is a linear combination of the X polarized light and Z polarized light with 1/√2 in the middle, right? So it's just 45 degrees rotated. That's all I've done. I've rotated this by 45 degrees. And the perpendicular direction is also 45-degree rotated, right? So what we have is, we have this X and Z directions, right? And we have rotated this by 45 degrees, and we have X prime and Z prime directions, right? It's just 45 degrees rotated. And this is just like a rotation matrix applied to them. Because we have quantized values, we're going to use two-dimensional vectors, right? So the X polarized light, we were saying that we were showing it by X hat, a vector in the X hat direction, and Z polarized light by a vector in the Z hat direction. The analogy with the spin would be that here we have a two-dimensional vector that we're going to call SZ plus 1, right? And this here we have a two-dimensional vector we're going to call SZ minus 1. This is when the result of SZ is +1 and SZ minus 1. All I'm saying is that I'm just going over this part, right?
Professor, is the
Yes.
X dash polarized light for the Z cap term, is it supposed to be KZ minus omega T?
Oh, sorry, you're talking about this? KY.
No,
Thank you.
yeah, okay.
Thank you so much. Yeah. I changed my notation halfway through from, that's why there are some Z's and Y's messed up. All right, so the X prime polarized light is just this X and Z rotated by 45 degrees. So this is the vector. And then the Z prime polarized light is this vector. This is also 45 degrees rotated. In analogy, we'll call SX plus 1. This is a vector, right? This notation, think of it as a vector for now. Plus 1 is this. I'm just adding these two vectors, right? And then SX minus 1, I'm just subtracting this term, adding them with a minus sign here. Is that good? So I'm trying to use the fact that the analogy between polarization vectors and I'm trying to use the analogy between this polarization experiment and the spin experiment to use the mathematics of polarization vectors to invent some mathematical framework, some vectors to describe the spin experiment. Good? So the analogy between polarization vectors and spin vectors sort of stops at this point, because polarization is either in the X direction or the Z direction. Polarization cannot be in the Y direction. Does anyone know why? Well, you go back to the
light
Sorry?
only has 2 degrees of polarization.
Correct, exactly. So polarization vector is always perpendicular to the direction of propagation of light. Yes. But as opposed to the polarization, spin is a three-dimensional vector, so there's Sy as well. Now we're going to use the rotation. To go from Sx, to go from the measurement of Sz to measurement of Sx, we just rotated our system by 90 degrees. We could imagine a change in the setup where instead of the particle propagating in the Z direction, we propagate in another direction, and we can design the experiment such that Sy is detected. It's actually good homework for you guys. To think about how to design such an experiment. It's not complicated, it's just a rotation. Now, what you find is that these Sy's, that as you have this experiment of Sy is also quantized. It's either plus h bar over 2 and minus h bar over 2. And these vectors, in analogy with what we had up here, should also be a linear sum of Sz plus 1 and Sd minus 1. And at the same time, a linear sum of Sx plus 1 and Sx minus 1. So what am I saying? What I'm saying is that this experiment that I described here, right? This that I described here, just replace, so here I was propagating in some direction and doing experiment Sx, Sc, Xy, right? Just replace all the Sd's with Sy, or Sx with Sd's. Just go through different permutations, and you learn that because of rotation symmetry, because you could rotate this experiment in different directions, you should have it should be the case that where was that? Yeah, Sx, Sy is also a linear sum of these two. All right. It turns out that there's actually a nice analogy with light as well. It's to compare it, you have to compare it with the circularly polarized light. This is a setup where your polarization vector is still in the X and Z direction. However, there's a relative phase, pi over 2, between the two, right? So if you just took this is something that we discuss in electromagnetism. So if you just took this equation and wrote it in terms of exponents, right? You end up with an, oops, there's a typo. You end up with an I here. Okay, so the analogy actually is complete if you try to make the analogy between polarization and spin, but you have to also consider this circularly polarized light, right? Where there is a phase shift between the X and Z. And then it gives you this I. For now, I'm just describing the setup of polarization of light. So the right circularly polarized light could be written this way. By analogy, I'm going to write the SY plus 1 this way with an I. So I'm just summing these two. And then I'm going to write SY minus 1 with minus I in between. This is an analogy with left circularly polarized light. So these are at the moment analogies, and to motivate this vector structure, these two-dimensional vectors. So the lesson we're learning is that no matter how counterintuitive that experiment, Stern-Gerlach experiment is, and it seems totally wacky that we could not simultaneously measure SZ and SX, but even though it doesn't make sense to us, we could still use complex two-dimensional vector spaces to model quantized spins and produce the prediction and produce answers that match the observation. So they explain the observations. In this context, measurements then corresponds to projections into these two bases, in these three bases. So we'll go through that slower in the next lecture. But this last bit of it, if you're asking what is measurement in this context, is just projecting these two-dimensional vectors to their components, right? But we're gonna cover this in more detail later. So what I just went through was the Stern-Gerlach experiment, and if I want to summarize it, is this simple experiment that teaches you that if you an electron or an atom, silver atom, has properties that could not be simultaneously measured ever. This is a fundamental law of nature, that you could never measure these simultaneously. And it seems like performing a measurement erases or messes up what you knew about the system, about the other property that you had observed before, right? So there's this, it's as if there's some sort of conspiracy going on. But we could model this in a very nice way, using the analogy of between silver atoms and spin and polarization of light, right? So that's the summary of what we've gone through. Any questions so far?
Why aren't we as surprised by this like lack of full information about classical EM as we are about angular momentum? Like, shouldn't we be as surprised that we can't know the circular polarization and the linear polarization at the same time?
I open that question to everybody. Why is that? Does anyone have an answer? It's a very good question. What you're getting at is an important distinction that exists in an important feature of classical physics. In classical physics, we think of particles as fundamental description of the theory, right? So, and particles, we attribute properties to particles. A silver atom is a particle, and it has spin in the S direction, a spin vector, Sx, Sy, Sz, right? Whereas in classical physics, light is a wave. Light is not a particle. If you viewed light as a particle, as we do in quantum mechanics, we view it as a photon, then you run into the same problem. As a matter of fact, the experiment that I just described, if you put next to what I just described, I said beam of light, if you just said the word photon as the particle of light, this analogy is exact. It's simply the fact that in classical physics, we don't think of light as being carried or having particles. It's just waves. Does that answer the question?
Yeah.
So this particle wave duality that people talk about is precisely making this analogy exact. Quantum mechanics tells you that there is no such a thing as particle. There is no such just particle. There's no such a thing as wave. There are two sides of the same thing. Light is wave and particle at the same time, as we're going to describe in the next experiment. And an atom, electron, a particle is that what we thought is a particle is also a wave at the same time, right? So that seems super crazy, but we're going to go through the second experiment precisely shed light on this particle wave duality. Is that good? Any other questions? All right. So actually, maybe I could make a longer pause. Any questions about Stern-Gerlach? If you had not seen Stern-Gerlach, by this point you should be perplexed. This is the core of quantum mechanics. And as we saw, we ended with this, well, a bunch of crazy philosophical conclusions, but let's put that aside. As I said, that's for your Sundays. You could think about it on Sunday. But now we're just talking about modeling it using vectors, complex vectors. We saw that we have to use complex vectors. We're sort of forced to use this I. We're going to come back to it later and see why there had to be complex numbers and couldn't be just real numbers. But we also ended with this thought that this analogy puts in, brings up, which is there a distinction between light as a wave and atoms as a particle, or are they related? The second experiment is precisely going to tell us that this is there are actually two sides of the same thing. Okay. The second experiment is called the double slit experiment. It was originally a thought experiment, but later on it was actually detected and observed. And I absolutely encourage you guys, if you want, just send me an email. I'll try to put the references. There are very recent experiments that have gone through this in gory details. Experiment 1, Stern-Gerlach, is explained in Sakurai. Experiment 2, I cannot stress this enough. You should definitely look up Feynman Lectures on Physics, Volume 3, Section 1. He goes through this double slit experiment with, it's a really fun read. And what I'm going to say is just a very quick summary of it because we don't have much time. But he goes through this as usual, like Feynman, it's fun. It's fun to read it. All right, so what's the experiment? Imagine you have a slit, right? So this is like a sheet with a hole here, and you shine light. And here you have a detector, right? And you see this detector detects, like if it detects light here, it will like click, right? So something will go off, right? And then you shine light and you just like do these measurements. Every time you send this through, you detect something and you plot the probability of these, or the number of times that these detectors have gone off. You do this, as I'm going to describe this experiment, I could talk about light or I could talk about an atom. It doesn't matter. As a matter of fact, the shocking phenomenon that we're going to see is mostly about a particle sent through, but you're going to see that also if you send light through, a wave through, it will also in some circumstances, it will behave like particles, right? So what comes in could be an atom, or it could be a beam of light, a photon, which is also a particle in a sense, right? Is that good? So if you send it through the first slit, you expect some like peak here in your detector, if this is the detector is counting. And if you have another slit here, you expect something like this. So P1 tells you about the probability of detecting, this is the Z direction, for example, the particle at any point. And P2 is another probability when the slit 2 is open only. Right? So P1 is the probability the particle goes through slit 1. P2 is the probability that goes through slit 2. Of course, there's Z dependent. So this P1 of Z is, for example, this point. Right? Good. Are there any questions so far?
If we're sending particles classically, why don't we expect a delta function? Like
Yeah,
Is
because
it a
all
distribution?
measurements have some accuracy. So there's a phenomenon
Okay.
called diffraction, which is associated with waves, right? But that actually happens to particles as well. And just for now, think of it as your question is very valid. As a matter of fact, because particles act like waves, there will be diffraction and there will be some width to this, and there's no way to get rid of it. However, for the purpose of this, think of this as a detector having some finite precision. Good. You could design this such that this is a peak. You could actually, as a matter of fact, you could design experiments that this could be arbitrarily peaked. Okay, now the experiment is called double slit because it involves having both slits open at the same time. Now, from your optics courses or your E&M courses, I don't know wherever you took this, you know that now the expectation from the particle and wave, the wave would now match the particle. If you send a wave here, what you see is an interference pattern. This interference pattern is not the sum of these two. It's not like, whereas if you had a particle, the particle will either go through 1, which gives you this, or goes through 2, which gives you this. So if you had a particle, the total count of the number of times and the locations that the particle is observed should look like the sum of P1 and P2. And if they're close to each other, it should be something like this. For a wave, you get something else. You get this interference pattern, right? So which one is it? So let me just say this very clearly. The distinction is that we think of a wave as going through both slits at the same time, whereas a particle can go through either slit 1 or slit 2. This either or means that you sum the probabilities, and the fact that waves goes through both at the same time leads to this interference pattern, plus some other wave behavior leads to this interference pattern, right? So the question is, which one do you see? Any guesses?
The wave interference pattern.
Exactly. So no matter what you send, light or particles, you see the interference pattern. So that is shocking because, as I said, if it raises the question, if it's an actual particle, it must either go through 1 or 2. It cannot simultaneously go through them. So what you should expect is this summation. So what is going on? So here's like, if you're a skeptic, you might say that maybe the particles go through slit 1 and 2, but somehow they talk to the particles that go through 2 and 1, they talk to each other and coordinate and conspire for such a behavior. But you could get rid of that already by the way I described the experiment. I described the experiment as sending a beam of a single particle. So this skepticism is valid if your beam contains more than one particle. You could just imagine if there's some sort of conspiracy going on, the particles that go up and down, they coordinate things. But this cannot be because we could do this experiment as I described the experiment using a single particle. Just we have a detector that sends a single particle at a time, and just we're going to measure the statistics of what we see here, right? So that can't be. Could it be that the particle splits in half? No, because we could make our detector, design a detector that detects whole particles, right? It could be, for example, a fundamental particle that could not be split in half, or we could discuss this in, this is the design of experiments. It's beautiful. Like they come up with all sorts of ways of just ruling out these crazy possibilities. So it seems like particles go through, as I said, if the particle picture is correct, they should either go through slit 1 or 2, so they should add up. But let's see, maybe we could, as we're doing this experiment, we could also look at it to see where the particles go through, 1 or 2. If we could actually look at it, then we have a very sharp contradiction, right? Because if a particle goes through, like let's say here, you could shine a beam of laser and scatter it off of it, for example here, and then know whether it goes through the top one or the bottom one, right? You could measure explicitly, directly, which slit the particle goes through, right? So here's an idea. what we're gonna do is that we're gonna send the particle through the double slit, and we're gonna watch it. Like for example, this as experimentally is a laser beam that is sent in, laser beam that's sent in. If it goes through, the particle goes through this hole, the reflection pattern is something that's different from the reflection pattern if it goes through this, and from that you could deduce which hole, which slit the particles goes through, right? So we should have a sharp contradiction there. Does anyone know what happens in this experiment?
It destroys the interference pattern.
Exactly. The moment if your laser is off, you see the interference pattern. But the moment that you turn on your laser, instantly it destroys the interference pattern. Now, it's interesting because here you could think of this measurement as some sort of in comparison with Stern-Gerlach. It's in the same spirit. This measurement messes up another property of another measurement, something that we thought was another property. So you could not, so if you try to pin down whether the particle is going through whether it's behaving like actually no, how do I say it? Well, okay, so maybe I'm trying to over-explain. It's incompatible to have the interference pattern and know at the same time which slit the particle goes through. So the moment you turn on your laser, the interference pattern is destroyed. You see P1 plus P2. Is the experiment clear? The observation? Okay. So the lesson is that atoms, as well as light, behave like waves as long as you don't measure their positions. When you measure their positions, they behave like particles. So the behavior of the object, particle, whether it behaves like wave or particle, depends on what you're looking at and what you're measuring. This is the so-called particle-wave duality. What we thought was genuinely wave, light, also behaves the same way as behaves the same way. Therefore, it also sometimes behaves like a particle that we call photon, right? Atoms, which we think of traditionally like in classical physics as particles, also behave like waves, and that's a particle-wave duality. All right. So in summary, what we went over are two experiments that put us in this weird position that it seems like we have to seriously revisit our principles of classical physics, where we sort of assume that particles are different from waves. Particles have a whole list of properties, and there is no, like how much you know about the properties depends on your measurements, and the better measurements you do, the more accurately you could know the values of those the values of those, could observe these properties in detail, right? Quantum mechanics tells you that this is not possible. We also, so this is what we saw in this lecture, we also saw that somehow we already know what mathematics we could use to model this behavior, because we have studied waves. So waves have already taught us how to do this, polarization of light, and it's by considering vector spaces that are complex and have a number of dimensions. So these are like complex dimensional vector spaces. The number of dimensions has to do with the number of distinct outcomes, because we said that the system is quantized, right? We saw that SZ is quantized, it's either up or down. Those are two distinct outcomes. Therefore, we use two-dimensional vectors. If you design an experiment where you first saw some quantized behavior, and the quantized behavior showed like D possibilities, then to model that, you will be using D-dimensional complex vector spaces. The D-dimensional complex vector space has a name, that's a Hilbert space. It's a D-dimensional Hilbert space. The two-dimensional one is a two-dimensional Hilbert space. However, if you're very math-oriented, the word Hilbert space usually means the infinite dimensional one. But physicists often talk about the two-dimensional Hilbert space, a d-dimensional Hilbert space. A two-dimensional Hilbert space is colloquially referred to it as a qubit quantum bit. A d-dimensional Hilbert space, that degree of freedom, we refer to it as a d-level quantum system or qdit. This is just a terminology. All right. Any questions? All right, let me stop sharing. Okay, so this is the end of lecture 1. This was a short lecture because I was planning on actually, oops, sorry, let me turn on my video. I was planning on talking to you guys a little bit about your background, but unfortunately Zoom is not the ideal setup. One quick question. So usually what I do is, even for in-person lectures, I usually prepare iPad slides and I go through it, and if there's something I go on chalkboard and explain it. Do you guys prefer that, or do you prefer a purely chalkboard class? Because I can do that as well. You don't have to say it now, but if you have strong opinions, just say it and I can adjust accordingly. The advantage of the iPad thing is that I could record it and it's very straightforward. Actually, let me stop the recording. But about how do I stop the recording? Okay.